So we were looking at one cylindrical coordinates or three-dimensional cylindrical coordinates fluid flow, and mainly we saw that the motion was developing in the x direction, in the radial direction, and it was changing between r equal to 0 to r equal to the maximum value, let's say equal to a, in the three-dimensional motion. And we considered the appropriate coordinates, which were cylindrical rectangular coordinates, r, u, and z. Remember, it's important to remember that normally the Navier-Stokes equation, which are considered to be equations of motion that completely specify a fluid flow in most general terms, are three-dimensional vectors equation. So we assume a general motion to be three-dimensional in nature, then we reduce it as appropriate depending upon the particular condition of the fluid flow. The velocity vector, therefore, will generally depend on x, y, z coordinates and time, because time is another factor that makes it steady or unsteady, and therefore its introduction, its involvement is essential, and it's a part of Navier-Stokes equation. Lower dimension flow reduce complexity of analytical and computational solution. If it is single dimensional or one dimensional, much easier to solve, although not always, but in most cases. Two dimensional level of difficulty has increased. Cylindrical, spherical, generally we take three-dimensional coordinates, and where appropriate, it's good to transform the equation of motion from x, y, z to either cylindrical coordinates or spherical polar coordinates, because those coordinates are meant for that specific geometry in which the fluid flow is taking place. Here we consider the same example that I have mentioned earlier, that where the fluid flow is developing in the pipe with a velocity v that is dependent on r, as we have seen, and it's a function of r, and also the pressure which will depend on z. The pressure in the fluid can also be calculated at a certain point z, whatever its value may be, and where the point of consideration is involved, and with a negligible error, because the motion in the third direction is almost ignorable, and that is not important. So these are the two more important things that can be considered in such a flow, which we discussed in our example, and I showed you the picture of. We consider a steady flow of a fluid through a circular pipe attached to some tank, and then the fluid flow that will take place is here that I had showed you earlier, and we were discussing its development along the line. And you can see that in the end, the velocity vector is only dependent on r. But somehow, if we have to apply the other parameter, pressure, then pressure will change with z. The pressure will have different value for different value of z. The fluid velocity everywhere on the pipe surface is 0, as we discussed, because of the no slip condition. No slip condition here refers to the viscous effect that exists between fluid and the solid body of the pipe in which the fluid is flowing. The flow is two-dimensional in the entrance region of the pipe, since the velocity changes in both the r and z direction. In the beginning, it's changing in the two directions, as we have seen, and the picture was showing clearly. but then the velocity profile develops fully and then it remains unchanged with respect to z. But however, even at that time, after a certain lapse of time, it depends on the value of r, and approximately this is equal to about 10 pipe diameters, 10 times, let's say, 2r, if r is the radius of the pipe that we are considering. This is just to make an estimate that how far from the beginning the fluid flow will develop to its complete form, and it will become laminar in its behavior. The fully developed flow in a circular pipe is one dimensional, since the velocity is now changing only with the radius r, and it doesn't change in angular u or axial z direction. That is, the velocity profile is the velocity profile is the same at any axial z direction, and it is symmetric about the axis of the pipe. Even the picture was showing the fully developed flow is very symmetric between the R line. Note that the dimensionality of the flow also depends on the choice of coordinate system and its orientation. The pipe flow discussed, for example, this was just to discuss an example and show some of the things, is one dimensional in cylindrical coordinates but two dimensional in Cartesian coordinates, illustrating the importance of choosing the most appropriate coordinate system. That is, if we have to choose xy rectangular coordinates to solve the problem, then it becomes two-dimensional after having fully developed. And if it is considered only in cylindrical polar coordinates, then it is changing only with respect to r at later time, and that means we don't have to consider the second dimensional. So a two-dimensional fluid flow becomes, or it is reduced to one-dimensional, and of course one-dimensional equations are easier to solve. As one can understand, solution of a linear equation is much easier compared to solution of a second order equation. Also note that even in this simple flow, the velocity cannot be uniform across the cross section of the pipe because of the viscosity or viscous effects that is taking place at the boundary. However, at a well-rounded entrance to the pipe, the velocity profile may be approximated as being nearly uniform across the pipe, since the velocity is nearly constant at all radii except very close to the pipe wall. A flow may be approximated as two-dimensional when the aspect ratio is large and the flow does not change appreciably along the longer dimension. When we are considering two-dimensional, if the flow, let's say there is r and theta direction, for example, and if at large r the velocity does not change much with respect to theta, or if there are xy direction and we are moving, the flow is moving in the x direction, after large times, if the movement of flow develops only in x direction and it does not change much with respect to y direction, then we can ignore the y component, and solution of x direction equation is sufficient to predict the flow conditions. So we will apply these conditions as appropriate when we come to it.